us have experienced scenario where we can model with the differential equations. What we'll share to you is a scenario where we want to model how quickly an object cools or heats up when it's hotter or colder than the room temperature. And the way that we'll think about it, it is the way that Newton thought about it. And it is described as Newton's law of cooling. Newton's law of cooling states that the rate of loss or gain of heat from a body is directly proportional to the difference in the temperature of the body and its surroundings. So let me write that in mathematical terms. So Newton's law of cooling tells us that the rate of change of temperature, I'll use that with a capital T, with respect to time, lowercase t, should be proportional to the difference between temperature of the object and the ambient temperature. So that is the mathematical description of it. And once again, it's common sense. Now I know one thing that you're thinking. You're like, okay, if the temperature is hotter than the ambient temperature, then it should be cooling. The temperature should be decreasing, and a decreasing temperature would imply a negative instantaneous change. So how will this be a negative value in the case where the temperature of our object is greater than our ambient temperature? And the way that would happen is you would have a negative k. If you don't like thinking in terms of a negative k, you can just put a negative right over here and now you would have a positive k. This is a separable differential equation. So we just have to algebraically manipulate this so all my capital T's and dt's are on one side. Capital T for temperature, lowercase t for time. And then I'm going to have all my time differentials and time variables on the other side. So one thing I could do is I could divide both sides by t minus t sub a. So if we do that, if we divide both sides by this, we are going to have 1 over t minus t sub a and multiply both sides times the time differential. So I'm going to have that dt our temperature differential times our temperature differential is going to be equal to negative k times our time differential. Now I can integrate both sides, and the integral of this is going to be the natural logarithm of the absolute value of what we have in the denominator. You can do u substitution if you want. If we said u is equal to t minus t sub a, then du is going to be 1 dt. So you could say the integral of 1 over u du, and so it would be the natural logarithm of absolute value of u. And this right over here is u. So this is the natural logarithm of the absolute value of t minus t sub a is equal to e raised to negative kt plus c. By using the logarithm rule, this e raised to the natural logarithm will be cancelled, leaving only the absolute value of t minus t sub a. We can write this as the absolute value of t minus t sub a is equal to e raised to the negative kt plus c. This is the same thing as e raised to the negative kt times e raised to c. And we could just call this another arbitrary constant. So this we could say is c times e raised to the negative kt. If we are dealing with someone that's hotter than the ambient temperature, where t is greater than or equal to our ambient temperature, so that means this is hotter, then this inside the absolute value is going to be positive. And then we can just add t sub a to both sides. And then we could have our temperature as a function of time is equal to c times e raised to the negative kt plus t sub a. So this is going to be our general solution in the case where we start with something that is hotter than the ambient temperature. And if we want to look at the case where something is cooler than the ambient room temperature, let's say T is less than our ambient temperature, then this inside the absolute value is going to be negative. So then this results to T sub A minus T. you can get the same value as when it is inside the absolute value. So that is going to be equal to c times e raised to the negative kt, and so then to solve for t, you could add t to both sides and subtract c times e raised to the negative kt. We will now have t as a function of time is equal to t sub a minus c times e raised to the negative kt. So this is the case where you have something that is cooler than the ambient temperature.
Wala, laot lang. Kunting inuman, kunting asin.
Oh, kaya ikaw may nasa itim sa itim. Tarungan.
Kaya ikaw tinawag ko kasi professional ka na dyan.
Hoy, si Kuan ba? Kailan mo to?
Ikuhan lagi.
Oh, sus! Saunahan! Ang labo. Na-discuss yan eh!
Uy, malaw. Ganong man?
Ay, kay Kuan, lambok na. Saan mo nagkupong pa? Nag-try.
Hindi na lang siguro tawag din naman eh.
Sige! Uyong ka din! Mautay na kayo dali! Dito, namatay ang sus. Stay. Just na naman.
Kung saan mo pa gamit na lang yung anak.
Kuan na, pang pabilib kasi.
Para imbita lang.
To gain some intuition on what Newton's law of cooling tells us, consider having a cup of coffee. We all know that the coffee will be too hot to drink for the first minute or so, but eventually, it reaches a temperature we can enjoy it at. We then can drink the coffee leisurely over say 10 minutes and it stays warm throughout. Newton's law of cooling states that, as the temperature of the coffee cools toward room temperature, its rate of cooling slows. This is why it stays at a nice warm temperature for much longer than it does at its hottest temperature.
You know that the water of this is normal, but when you put that, it becomes cooler. Okay ah? Tuos ako. Hindi ka mo tuos. Mamatay ka na.
Ano ba?
Ang imong temperature karon, pag mamatay ka unya, maubos imong temperature, umabot na ka.
Tagay.
Init.
Tagay.
Init.
Tagay. Cheers.
Init. Unya, bugnaw, patay ah.
Cheers. Ugnaw kayo. Ano ang gagigong mo na ugnaw na? Ano problema, pre? Wala, pre.
Break your jaw!
Wala yung...
A few moments later.
Patay! Patay! Bugnaw! Init ganina! Karon! Bugnaw! Bugnaw! Bugnaw!
So we prepared 3 sample problems for us to solve. The first one is a scenario where the temperature is decreasing. After 2 minutes in a room at 70 degree Fahrenheit, the coffee has cooled to 165 degree Fahrenheit. Find the time that it will take for the coffee to cool to 120 degree Fahrenheit. So first, we have to determine the given values. So the final temperature is 165 degree Fahrenheit. Ambient temperature is 70 degree Fahrenheit. The initial temperature is 180 degree Fahrenheit and the time is 2 minutes. So now, let us determine the required value, which is the time when the temperature is 120 degree Fahrenheit. So to solve this, we have this formula. The final temperature minus ambient temperature is equal to the quantity of the initial temperature minus ambient temperature multiplied to e raised to the negative kt. So next is we have to substitute the values to the given variables. 165 degree Fahrenheit minus 70 degree Fahrenheit is equal to 95 degree Fahrenheit is equal to the difference of 180 degree Fahrenheit minus 70 degree Fahrenheit, which is 110 degree Fahrenheit times e raised to negative 2k. So e raised to the negative 2k is equal to 95 over 100. So k is equal to the natural logarithm of 95 over 100 all over negative 2. So we now have the value of k. Next is we have to substitute the numbers. So time is equal to the natural logarithm of 50 over 100 all over the natural logarithm of 95 over 100 all over negative 2, which is approximately 10.76 minutes. So the next one is a scenario where the temperature is increasing. So a cold pineapple drink is poured out at 50 degree Fahrenheit. After 2 minutes of sitting in a 70 degree Fahrenheit room, its temperature has risen to 56 degree Fahrenheit. What will the temperature be after 10 minutes? So now, let's determine the given values for this problem, which is the final temperature is equal to 56 degree Fahrenheit, the ambient temperature is equal to 70 degree Fahrenheit, the initial temperature is equal to 50 degree Fahrenheit, and the time is 2 minutes. So now, let us determine the required value, which is the temperature when time is equal to 10 minutes. So to solve, we will also use this formula. So let us substitute the variables in the given formula. So now that we have the value of k, let us now determine the value of temperature when the time is equal to 10 minutes. So T is approximately 66.6 degree Fahrenheit. So our third problem is actually how Newton's law of cooling helped in forensic science. At 10:07 p.m., you find a secret agent murdered. Next to him is a martini that got shaken before he could stir it. Room temperature is 70 degree Fahrenheit. The martini warms from 60° Fahrenheit to 61° Fahrenheit in the 2 minutes from 10:07 p.m. to 10:09 p.m. If the secret agent's martinis are always served at 40° Fahrenheit, what was the time of death? So we will first determine the given values, which is the final temperature is 61° Fahrenheit, the ambient temperature is equal to 70° Fahrenheit, the initial temperature is equal to 60° Fahrenheit, and the time is 2 minutes. The required value is time when the initial temperature is equal to 40° Fahrenheit. Using the same formula, we will now substitute the given values. So our value of k is equal to the natural logarithm of 9/10 all over -2. So now that we have the value of k, let us now determine the time when the temperature is equal to 40° Fahrenheit. Time is equal to the natural logarithm of 1/3 all over the natural logarithm of 9/10 all over 2, which is approximately 20.85 minutes. So from 10:07 p.m., the agent was murdered at approximately 9:46 p.m.